We are getting now to our final presentation, GBeam Composite Bridge Girders, results of recent research and new developments. It's given by my colleague, Dr. Bill Davids, the professor of civil and environmental engineering at the University of Maine, where he teaches classes in structural design, structural analysis, and numerical methods. He was a bridge engineer for 4 years prior to entering academia in 1998. We came together with Bill that year here at UMaine, 25 years ago. Bill has directed research in bridge engineering, inflatable structures, composite materials for infrastructure applications, and the mechanics of solid and engineered wood. He has co-authored, co-authored more than 60 articles in peer-reviewed journals, co-holds 4 patents, and has developed several finite element analysis packages used in industry and academia and transportation agencies as well. Bill holds a PhD in civil engineering from the University of Washington, Bachelor of Science and Master of Science degrees in civil engineering from the University of Maine, and he's a licensed professional engineer. Welcome, Bill.
Thanks, Roberto, and thanks to the first 2 presenters. And I got to warn everybody, I mean, I am a structural engineer. No equations, I promise you that, but you're going to see some data, you're going to see some research results. And I want to talk about the GBeam. You've heard about it a lot today. It wasn't my intent to have it be so present and everything, but that's okay, because my talk is going to be very different. I'm going to review the concept, initial research, and application just to orient everybody, and coming from the engineering perspective and the structural side. And one thing I want you to note is that's 2016 to 2020. And one common thread I want to weave through this is deployment. We heard a lot about implementation of research this morning and how hard it is, and it is really difficult. And you're going to see how it plays into the research here. But the fact that that happened over the course of 4 years never fails to amaze me. That's very, very fast. But as a result, there's still a lot of work we have to do, which is what the bulk of the talk is going to be about. That first part is really going to set the stage for what don't we yet understand? What else do we have to work on still, and why? So the anatomy of a GBeam bridge, it's just a girder bridge. That's all it is. You look at the rendering on the upper left, we've got these composite tub girders. They're composite with a concrete deck. They're direct replacements for steel or concrete girders, and you've heard the reasons for that several times. They're lightweight, they're corrosion resistant, and they're potentially also more environmentally friendly. They're currently used for simple spans, or really applicable for simple spans up to about 100 feet. That's where they sit. There are a lot of bridges like that around, but that's not every bridge in the world. So we tested our first prototype. It was almost 5 years ago to the day in 2018. So we started the design and the development. I think I skipped a slide there. There we go. Okay, it went by itself. All right. So when we talk about an FRP girder versus a steel girder, how many bridge engineers are in the room? Raise your hands. Okay. So you design a steel beam. You got 3 limit states. You got moment, you got shear, you got deflection. You play with yield strength. You play with dimensions. You might add stiffeners to the web. That's all good. We have the same 3 limit states for the FRP girder. The difference is now we've got a hybrid composite here. We've got carbon fiber in the bottom flange, high modulus, high strength for tension. We can play with that to increase the bending strength and stiffness. Our webs are FRP face sheets with fibers oriented at plus minus 45, which is optimal for the shear. We have a foam core in the web to increase the buckling resistance, because that's another limit state. With a steel girder, we could add weld stiffeners to eliminate buckling. With a composite girder, we can't weld anything to it, but we can change the thickness of that foam core. And we have to control deflection as well. And we can do that applying the same mechanics principles and bending concepts we do with a steel beam or a concrete beam. We went through that process several years ago. There we go. And we did our first girder test 5 years ago, almost to the day, I think, in 2018. And we loaded it, and it was rather nerve-wracking. It was a 40-foot girder. We weren't sure how it was going to work out. It worked out really well. It carried 2.65 times the factored AASHTO strength 1 live load, which is very large. It might seem too large, but it actually was about where it should have been because of the large factors of safety we implement when we design these systems. Its stiffness and strength were well predicted. We're very happy with that result. And we very quickly went on to build our first bridge, which you've heard about today, the Grist Mill Bridge. just a mere 2.5 years later, it was completed in the midst of the COVID epidemic. 75-foot span. John knows right where it is. He drove over it the other day on the way here, but he wasn't quite sure, but I told him, and he did go over it, right? US Route 1A in Hamden, Maine is about 12 or 15 miles south of where you're sitting right now. AIT Bridges, our industry partner, designed and fabricated those girders. The only reason this happened so quickly, there are two reasons. Number one is the Maine DOT, who was willing to say, look, we will use a GBeam here. And our partnership with the Maine DOT is strong. Our relationship with them is good. And their confidence in us and our good working relationship with them was critical. The other thing was we had an industry partner in AIT that had already commercialized the concrete filled FRP tubes, and they were in position to take that technology, license it, and fabricate those and take on the design responsibility. If those two things hadn't been in place, this would not have happened, at least in 2020. It might have happened in 2024. I don't think it's an exaggeration to say it would have been another 4 years or so. The other thing I want to point out is all this initial work was funded by ERDIC. We've got Jay's here from ERDIC right now. This is an example of the U.S. Army funding a technology that they saw promise for for their needs, but they also support commercialization of this. And they want to, it's fine when you take this out into the private sector. So that was really vital as well. Now, we went out and field load tested it right away. I mean, the day before we opened the bridge to traffic right away, which was the 31st of December, which is not when you want to test a bridge in Maine, but we got lucky and there really wasn't any snow on the ground and it was okay. We put some big trucks on there. We measured the response and everything looked good. It behaved the way we expected it to. There was a fair amount of conservatism inherent in the design, presumably from what we saw, but we could explain why that was, and it's always good to be a little conservative. And this was happening so fast that we didn't really build grist mill with all the details we would have liked. We were working simultaneously on a better way of connecting the concrete deck to the girder. We came up with this concept of infusing ridges in the top of the specimen. You can see there, that's a girder. Jay, that's one of the ones we shipped to you, actually. We made that in our lab last summer and sent it off to ERDIC to close out a project with them. You infuse those ridges and you interlock the concrete and the FRP mechanically. And now you can suddenly use, instead of a bearing type shear connector, a simple, at every foot on center, you can use stainless steel rod or mild steel. Stainless steel rod opens the door to a completely corrosion-free superstructure. It's a much better shear connection. I had a grad student working on that in parallel with grist mill being designed and put out in the field, but we couldn't bring those two things together in the first project. And at this point, that's what's been used on every bridge constructed subsequently. It's a better way to do it. But now we have to step back and we say, okay, we've got 4 GBeam bridges out there. There are others in the design phase, but we have to understand that we've tested one beam in our lab to failure. We have one strength test for validation. It was really focused on flexure, not web shear. Girder architecture and fabrication methods have been changed. We haven't looked at fatigue. These are important issues in any structure. We've done one diagnostic field live load test. One bridge we've gone out in the field at this point. We put trucks on and measured the response. How many steel bridges have we tested in the field? How many concrete ones? I personally have overseen something like 3 dozen tests just in Maine, and more than that in Maine, of course, have been tested, and across the country is thousands or tens of thousands, of course. And we have to design for both moment and shear, but in 2020, we were only looking at flexure. That's all we were reading were flexural strains. We were focused on bending. And another important question, can we build a multi-span GBeam bridge that's continuous for live load? So right now we're looking only at simple spans, and most of our bridges that are more than one span are continuous for good reason, because we get much more stiffness out of it. We better utilize the material. It's more efficient in terms of strength. You get better road quality. You don't get degradation of the joints because you don't have joints in the pavement where stuff can get through down there. So we'd like to look at a continuous structure as well. So with all these things in mind, we said, well, we've got to tackle these issues. And that's really what we've been working on for the last 3 or 4 years. And we start with web shear. And this was a really nice project funded by the Maine DOT, that again, are a really important partner in all of this. Understanding, we really have to look at these things. We've designed conservatively to date. We're comfortable with that, but we really need to understand what's happening. And what we need to realize is that all of our shear strength for the data for the web was coming from essentially a flawed test, D3518, which is a tension test of a plus minus 45 FRP, which doesn't produce pure shear. It's been criticized for that. It tends to underpredict the actual shear strength. So we made a pretty significant investment in what's called the picture frame testing device, where we can take a 1 foot by 1 foot panel of the web with the foam core, and we can put pin connected bars on all 4 sides, put it in pure tension and produce basically pure shear. And you can see the really nice shear strain field on the right from the digital image correlation data there. And we ran a dozen tests on a particular, a typical foam core panel for the web. And it actually showed that we got a shear strength on average, a lower bound mean of about 18 KSI. That's 80% higher than what we had been using in design. So that's good news. Our designs were indeed conservative. We can sharpen the pencil a little bit. This is well worth knowing, okay? But it's also important to know that it's not just the strength of the web in terms of the material, it's also the buckling capacity of the web, right? So the bridge engineers out there know that if you're designing a steel plate girder, you got to check for buckling. And it's a D over T ratio in the web, and you go to AASHTO and you look up a formula, and it's based on work by Stephen P. Timoshenko from 1930. And if you're not familiar with that name, trust me, he came up with all those equations back in the day. And you do this closed form calculation, and it tells you what the strength of the web is. And you might add some stiffeners and if you need to and go on your way. FRP, no, you have a foam core, you have quasi-orthotropic face sheets on there. Ask a practicing engineer, what's the buckling strength of that web? And you're probably going to get a blank stare. That's what you get from me. I don't know the answer, right? So, but practicing engineers have to be able to predict this. It's another limit state you've got to look at. So as part of that project, Andrew Skank, who's sitting here today, and I worked on this, he's been my partner in crime with a lot of this, dove in and did a whole suite of hundreds of finite element analyses, parametric studies, where we could get the buckling strength of the web from basically an eigenvalue analysis. And we could distill it into these simple design curves. The sample is shown on the lower right, where you have the strength of the web as a function of the ratio of the thickness of the core of the web for different face sheet thicknesses. That's the kind of tool that an engineer can look at and say, bang, okay, 20 kips per inch. That's the buckling capacity of my web. Off I go, I can do the calculation, okay? And that's important from an implementation point of view. If we don't have tools like this thing's not going to get accepted. Engineers have to be able to understand what's going on and have tools that allow them to quantify capacity. So then coming back to the fact we've to date only tested 1 girder. Well, we need to test some more. We're in the midst of that right now. That's ongoing in 2023. These are really interesting tests. And so we've got 2 beams in total. One we've already tested. We'll get to that in a minute. 38-foot spans. They're nominally identical to the girders that were used to build a bridge last summer in Westerly, Rhode Island. So these are full scale, nominally identical, except for one really important detail we'll get in a minute, to what's out there in the field. They have the ridge shear connection with the threaded rods. They're more heavily instrumented. So these are very, very practical tests, but we've got 150 channels of data on there, plus digital image correlation for strain measurement on the exterior. There's all kinds of stuff going on. I've only barely begun to sort through the data. We tested our first girder to failure in February. And there's a picture of it in our load frame post failure. And if you look at the picture on the lower right, you can see that's near mid-span between the load heads. That's tensile fracture of that carbon in the bottom flange, which was the expected failure mode. Subsequently, we got crushing of the concrete deck, but that was driven by the fact that the carbon failed and then the beam drove down. The concrete strains are not high enough to cause crushing. First is the primary failure mode. So that was in line with expectations. And I said, we got a whole bunch of data. Here's data from one channel. Okay, so this is load deflection at midspan, the most intuitive thing to a structural engineer. And so it's total load, midspan displacement. And we ran it through a few load cycles here. We went up to AASHTO service 1 and then strength 1, drove it all the way to failure and got to 313 kips, okay, which exceeded our prediction by well, 10% or so. We predicted 280. Okay, so that's good. We're predicting a little on the conservative side, but very reasonable. And overall, the performance was excellent with that. It was what we'd hoped to see, what we expected to see. And we carried 2.32 times the AASHTO factored moment, very similar to what we did with our first girder, which is 2.65. And the difference between that is we now design with a slightly smaller factor of safety. That just reflects new industry standards. That's the only reason for that. Now, the ridge shear connectors did well. They were pushed well up beyond typical factor demand. Same thing with shear. We did see a little bit of web buckling in the very first beam we tested. It's not clear if that came pre or post moment failure. We didn't see anything like that in this second strength test. But the strength test is the easy test, okay? The hard test is what we're doing now, which is the fatigue test, all right? We have not yet fatigue tested one of these full girders. We're in the midst of it. We have a specimen in the load frame. If anybody went on the tour the other day or is going on it tomorrow, you'll see this thing, 0.5 hertz, one cycle every 2 seconds. Moves about like this, okay? And we've got to apply 3 million cycles to that thing. And that's not an arbitrary number, because what we're actually assessing here is what happens when that bottom flange, we have carbon. Carbon's expensive. We pay a lot of money for that. That's our tension carrying portion of the girder. We don't want to use all the carbon over the entire span. We want to drop some plies in regions where there's low moments. We have 3 zones in the girder, and we're concerned about, or not concerned about, we're assessing where we go from 4 plies at midspan to 2 plies a little further out. And that is exactly analogous to what we do with a steel girder all the time, where we reduce flange width or flange thickness. And AASHTO would call that a category B fatigue detail. And assessing the capacity of that for fatigue requires 3 million cycles at the fatigue 1 load, which is what we're putting on that. Okay, and there's a lot of detail underneath that, but that's how we have to approach this problem, through analogy to materials we already know, because there's nothing about this in our codes, right? But this is language that bridge engineers understand, and ultimately, if we test to these standards, it can be explained to them, and they will accept. I come back to, again, the implementation and wider deployment of this. We always have to keep that in mind with our work. So, and we've been busy out in the field, live load testing as well. That's occurred over the last couple of summers, most recently this June. John Pinkham's back there. He's a current master's student working with me. I should point out that Jacob is a student right now as well, and he's the poor guy that has to babysit that fatigue test. So every time something goes wrong, he's got to reset the LVDT or come to my office and tell me what's wrong. But you're doing great, Jacob, don't worry. John gets to go out there in the field with Andrew and do the field load testing. And John's in the position, enviable or unenviable, of having lots and lots of data and another year to go, right? So we've gone out in the field recognizing that our first test was just flexure. And we started last summer, we said, look, we tested that bridge. It was brand new. I mean, it hadn't been open to traffic yet. Let's test, and it was in the winter, and Maine in the winter is very different than the summer. And we saw some interesting things, end fixity because of soil structure interaction with the abutments. Sorry, let's go out there in the summer and test it a year and a half later under warm conditions. Does it behave the same? Has there been a change in the structure? The good news is no, there really hasn't. It's behaving almost exactly as it did before. Then we said, look, we've got to get data on shear. We really need to understand what's happening here in shear. People rarely test for shear when they field load test a bridge. So we tested both the Grist Mill Bridge and another GBeam bridge that was built a few miles away in Hamden, Maine, a couple of years later in June. And that was focused on live load shear exclusively. And here's a picture of some of that testing. You can see now we've got 4 trucks on the bridge, and we've got them backed up to each other, and those heavy axles are right back towards the support where we're gonna produce the most shear. And we've got instrumentation there at the support. And that's a picture of Keith Barabee. Keith, you here? Yeah, Keith. Poor Keith. So he was our partner in crime. We needed somebody with expertise in a particular type of instrumentation. If you need help with instrumentation, he's the guy. Okay, go ask Keith. And it was raining kind of hard that day, but Keith was lucky. He was under the bridge the whole time. So we got some really interesting results out of that test. Didn't expect it. Not bad, but this is the reason why we do this stuff. Here's a picture of what's happening in the middle girder when it's loaded most heavily for shear. And first thing you see, look, focus on the red curve. You see these plateaus, right? So this is strain versus time. Each plateau represents, oh, we just drove a truck on the bridge. Drive a second truck on the bridge. Drive the third truck on the bridge. Drive the 4th truck on the bridge. Then all 4 trucks sit there, and it just holds there at the peak strain. That's all that means, okay? But those are 2 webs in 1 girder, and what do you see? The strain differs by 40, 50%. Okay, there's a so there's 2 webs in 1 girder undergoing very different shear strains. And that, I believe, is absolutely a consequence of the fact that these girders compared to steel or especially concrete are relatively transversely flexible, okay? Each individual web is impacted pretty heavily by the wheel loads that are closest to it, not so much by the ones that are further away. And there's also a little bit of skew, 15-degree skew, so there might be some torsion there, but I don't think there's a lot of torsion because the loads were really focused at the support. So here's a picture that helps illuminate that. This is the same data for every girder, okay? So you're seeing a bar chart of the strain in each web of each girder on the bottom. And the top picture is a cross section. It shows where the truck axles were located, where each pair of wheels on the tandem was located transversely. And you see the 443 is the most heavily loaded one. That's getting a lot of load from one pair, some load from another pair. The one that's 285 has the wheels right over it, but because of the rotation of the girder and the fact that these things are transversely flexible, it doesn't actually draw as much. And I won't go into it, but part of John's job is to build some really detailed finite element models of this to try to help explain it. And they do explain it. They pretty much tell us exactly what we're seeing here. But this is something that in the future, if we are to develop design provisions, we need to bring into play. We need to take into account the fact that webs carry differential amounts of shear in these girders, not something we typically account for in a regular steel or concrete girder. Another topic I'll briefly touch on is live load continuity. This one's still kind of a twinkle in my eye, I think. We're close. We might be there soon. But you know, when we do this all the time with multiple span steel or concrete bridges, we don't make many simple spans. We make them continuous for a very good reason. But we can't, you know, with steel, we just have splices out near the quarter points and we bolt them and it's all good. And with concrete, we can pour concrete and add a little rebar. Those are not options with FRP. How do you connect two FRP girders together? And the answer is not we glue them together and call it a day. We absolutely are not going to do that, okay? So what do we do? Well, we have this ridge shear connector, and I think that there's potential to make this work by actually roughening the interior surface of the girder, infusing the ridges on the interior surface of the webs in the bottom flange, and then filling some portion of the girder near the pier with concrete and transferring via shear the tension and compression that you get in the top and the bottom of the girder from the girder to the concrete, and then adding extra rebar over the pier for tension, which is what we do with concrete. We add extra rebar up there. So it really mimics what we do with reinforced concrete all the time. But there's some important questions. You know, what length of concrete infills are required? How effective will those ridges be? Can we actually carry that moment to the pier with that concrete plug? And we've started to look at this. And we've done some pretty detailed finite element models that indicate, yeah, I think this is feasible. I think with about 8% of the span length at each end infilled with concrete, additional rebar in the deck, the indications are, we know what the strength of those ridges are. We've done all kinds of testing on that interface, and our calculations show it ought to work. The stresses predicted by the finite element model show it ought to work. But I do believe that we need to do a test. This is another test. That's why I say it's a twinkle in my eye. I'd really like to experimentally verify this. The final thing I'm going to touch on, and we come back to implementation. I mean, I think this is a solid body of work, and we're hitting the right things and we're addressing the important issues. But if somebody can't implement this via a design guide, a code, something that explains to a structural engineer how to compute the moment strength, the shear strength, et cetera, it's never going to fly. It's not going to fly, right? So the DOT, we can design a bridge and we can put it out there. And then in 5 years, they're going to get a request for a permit truck and overload vehicle, and they want to assess the strength to know if it's going to be okay. They have to be able to do that, okay? So they have to load rate bridges in the future. They have to be able to do these calculations. So we have been working on a design guide. It's a draft. It's a work in progress. Andrew Skank has really been important in that effort. It's got flexural design provisions, shear design provisions. The girder deck shear connector, it's got design examples that show how you do these calculations. One thing is still missing is live load distribution. One thing a structural engineer wants to do is go calculate here, how many lanes of live load does a girder carry? We don't have those rules for FRP girders. We are trying to take the field test data we have combined with some parametric studies, FP models, to develop our own live load distribution factors to feed into this. That's kind of the final piece of the puzzle in this design guide. The long-term goal, of course, is to get this up for AASHTO approval, but it's not ready for that yet. So at this point, I'll wrap up. I apologize for running a little long, but I think we had lots of time left in the session regardless. And in conclusions, you know, I think our ongoing recent research has confirmed expected performance. There have been a few surprises, but nothing that is of any concern or shocking. That ongoing fatigue test is about what, 350,000 cycles, Jacob? 365. Okay, you must have it on your phone right now or something, right? So excellent. So, we're a little over 10% of the way there, expected to be done sometime in late September, probably early October, realistically. The differential web shear strains are something we really, we have to bring that in to how we analyze these things. Continuous bridges, I think, is a great opportunity. Little work to be done there. Design guide development, I believe, is really important for broad acceptance. And ultimately, if this technology continues to see the rate of application it has, I think we'll get there. So thank you very much for your time. I appreciate it.